All right, so we have this problem here. Now, this problem, um, 8.3.10, which I hope is your problem 20. I'm assuming it is. You didn't mention which numbers um, you're referring to, but um, as in 8.3.10, but hopefully this is the right one for your problem 20. For this one, we have a different type of set of data. First off, we have raw data. I mean, that's one thing. But the main difference is that there's a natural pairing. So student one, we have a score, first test score, second test. So there's a natural pairing, a dependence based on the before and after of each student. So each student has two scores. So the dependence by the student. So we're going to be performing a whole different hypothesis test. We've seen this hypothesis test before. This involves taking the difference of so as you can see, the null and alternative hypothesis is completely different. So let's look at this here. The table below shows the critical reading scores for 14 students the first 2 times they took the standardized test. So without the following alpha, is there enough evidence to conclude that their scores improved? So improved is telling you that the difference is going to be less than 0. The difference, because you take the first score and subtract the second score. So keep that in mind. We can copy this into StatCrunch. And just to go into this a little bit more, just how you get the difference is less than 0. Think about what it means for the second. If they improved, the second score will be higher than the first score. So if you take the first score and subtract the second score is, if they improved, the second score on average should be larger. So you're taking a larger number from a smaller number. So it's like, 3 minus 5. 3 minus 5 is a negative, is less than 0. So the difference is going to be less than 0. So the alternative hypothesis is your claim. Okay, so hopefully that makes sense. We kind of skipped this first part. The claim: the students' critical reading test scores improved the second time they took the test. So that's just taking this exact wording here. All right, so find the critical values. As usual, we should be using the, similar to the previous video on problem 19. We are interested in using the T calculator. Now, in this case, the T, we have a one-tail test. I mean, that's one thing. So, so actually, before we actually use this data to do the hypothesis test, we don't actually need the data to find the critical values. We're going to go to calculators, T. Now, keep in mind we're doing a left tail test. So a left tail test, we want, less than. And we want to look for alpha, which would be in the left tail, and that's 0.01 is our alpha level, as mentioned right up here. So we want that left tail to have an area of 0.01, and I didn't put the degrees of freedom in. The degrees of freedom in this case is n minus 2. So actually, let me double check that. I can't remember if it's n minus 1 or n minus 2 let me double check. So I actually looked it up, and it's n minus 1. So it's the amount of pairs, 14, and we're going to subtract 1. So that would be 13. And we compute. Oh, sorry. 0.01. Okay, so now we compute, and that's how we get the value right here. negative 2.65, 0, it's going to round down, because that's 3. And the critical region, what they're asking about next, is is this red portion right here. So it's less than negative 2.65. So there we go, right here. And the calculate d hat and SD, S sub d, that we'll need to do by actually doing a hypothesis test. So we want to do a t-stat, but we want paired because we have paired data. Sample 1, first test score. Score in second test, it's sample 2. And that's how we want it, score in first test, score in second test. And the difference is defined as the first test minus the second test. That's exactly what we want, as mentioned before. And we want this to be less than, as mentioned here. We want less than right here. And that's it. And so we want the mean. That's how they get negative 6.357. And they want the standard deviation. And we mentioned this before. And I showed you that we could actually copy the paired here and find the descriptive statistics for what would be in variable 4 for the differences. We did that before. But you can also take the standard error and multiply that by the square root of n, so 14. So we can take 9.1, yeah, we'll just do it this way. So I'll just pull the virtual calculator really quick. Okay, so we would take the standard error, let's clear that out, 9.1011454, and we multiply that by the square root of n, so that's 14, times the square root of 14. We've done this before, and we get 34 and that 0.053. So that's that value right there. Or I'll show you both ways. You could also, oh, actually we want that. Edit and save differences. If you choose save differences, then you'll notice that it'll copy the differences. I can't move it over, but in that next column. There we go, differences. And if we exit out of here, we can actually, to find the mean and standard deviation, we could actually find the descriptive statistics on this column right here. So stat, summary statistics, what they call it here, columns, and then we want differences and compute. And there's the standard deviation. That's another way of finding the standard deviation of the differences. That's what S sub d is. It's the standard deviation of the differences. This is the mean of the differences, which you can see right here. So two different ways of finding it. This second way is probably the easier way of doing it. Not you don't have to remember to take the standard error and multiply it by the square root of n. But anyways, we need to go back to the paired t-test, and we want, let's see here, where are we? Use the t-test to find the standardized test statistic. There we go, it's right there. Round appropriately, and then we want to determine if it's in the critical region. As we can see, this is not in the critical region because it's not less than negative 2.65. So we fail to reject the null hypothesis and interpret your decision appropriately, and that's how you go about doing this. So let's go to the interpretation. There's not enough evidence that the student critical scores improved, so make sure that it's addressing the claim. Remember, here's the claim here. Make sure it's directly addressing the claim. So we don't want to change the wording like they have here. Sample size not large enough. That's ridiculous. So the students' critical reading scores improved the second time they took the test. There's enough. No, it's not. There isn't enough evidence that they improved because we failed to reject, which supports the null hypothesis. So it supports that they are equal. So yeah, the option C is the only way to go here. Okay, so let me know if you have any other concerns, and I'll be more than happy to help.